Application of integration, density. Essential question, can I use density in the context of length, area, or volume to find mass or amount of quantity? Take a minute to stop the screencast and read what a density function is. Let's take a look at linear mass density. If we wanted to figure out the total mass and we knew the linear mass density and the length, we could multiply those together. For instance, the length were 10 centimeters and the density, this Greek letter is called rho, 9 grams per centimeter. We can see if we multiply these two, the centimeters are going to reduce and we're just going to end up getting grams. But let's consider a rod that's extending along the x-axis whose density is continuous and it's dependent on its location on the x-axis. So if the density is changing, maybe it's becoming more massive as we go further and further out, then we've got to take a look at going into little pieces. So if we take the rod and we divide it into little pieces, and we say that this little piece is fairly constant, it isn't changing much compared to maybe this piece over here that has a different density versus this one. And that's what we're going to do. We're going to set up a Riemann sum where we see that each little piece is operating on the constant density. All right, when we do this, we're going to have a lot of little pieces of masses, and each mass is represented by its own density and its own little length. And when we sum these up, we're going to get an integral. Okay, let's do an example. The Massachusetts Turnpike, and let's take a look at its density in terms of people per mile. So the farther you go out from Boston, the less and less people per mile there are. So what we're going to do is we're going to take a little piece right here, and this will be the length, and this will be the density, and we're going to multiply those two. When we multiply those two, that's going to be the number of people living in that little portion there. We're going to add up all the other little portions here and sum them all up and allow our little piece, our little change to go to not zero, but to go to zero, not to infinity. And then we're going to set up our integral. Now it's going from 0 to 5 because we're going within 5 miles of Boston. All right, so now we have a specific density here. So again, our little piece of population is going to be our density, which is f of x, times our length. And our density here is 500 minus x cubed, and this is people per mile. And remember, this little piece is miles, and when we reduce, we're going to get people. We're going to sum up all these little pieces from 0 to 5, 500 minus x cubed, and then we're going to say dx. And our result is going to be the number of people. Let's take a look at another density problem in terms of 2D. This is a 200 by 300 meter patch of ocean, and we have the shore right here, and we have lots of sharks closer to the shore and less sharks farther and farther away. So this is the shark density, number of sharks per square meter. We're not talking about a length any longer, we're talking about an area. So what do? Well, we're going to divide these areas, and we're going to divide them lengthwise because this is nearly constant. There are more sharks here, and then this density is going to be a lot less than this one right here. So this is the way we're going to divide them. It's going to be the area of the slice times the density, and then this is in reference to how far you are from the shoreline. So this area right here is 300 times the little thickness, delta x, times the density at that distance. And we're going to sum them all up, and we're going to take it to an integral, and it's going to go from 0 to 200 because that's where the rectangles are going from. If we want to have a specific density, let's say this, then we're going to replace that f of x with this density, and then we'll get this. And this is the this is the estimation of the number of sharks in that rectangle. Let's go to a 3D idea, and we'd like to find the mass of a cylindrical column of air 2 meters in diameter and 25 kilometers high. All right, so we have 1 meter here, and what we're going to try to do is find the volume here, and this will be pi r squared times delta h, and r will be 1. We'll go on to the next line, and then we're going to go to the volume times the density, and the density I'm just running is f of h so far. And remember, we did find this volume, and volume is in meters cubed. The meters cubed will reduce with this, and then we'll get kilograms. So this will represent the total mass. We're going to go from 0 to 25,000, and that's because we're changing the 25 kilometers to meters so that everything is in the same units, because our density was in meters. Another situation in which we use density is radial density function, where the density is pretty much the same in the ring right here. And so this ring will have the same amount, and this ring will have the same amount. What we're looking for is dividing the area that we're looking at into little pieces of area that have the same constant density. Now, what would that happen? That would happen with population. If this is the center of town, as we go farther and farther out town, there's less and less people. So this would be a perfect way to describe it. Okay, so remember the ring right here, its area is going to be described as the circumference times the thickness. So this will represent the area of the ring, and then we'll have the population density. And so when we multiply that, that's going to represent one of the rings. And you can see the population is dependent on how far away you are from the center. So this is the way the population integral looks like. 2 pi r times the density times that thickness. All right, here's an example of computing total population. We want to find the total population from 10 to 30 kilometers away from the city center. Let's take a look at the population density, and let's get more comfortable with it. This is 15 divided by root 1 plus r squared. And the population at 10 will be equal to 15 over, and if I put 10 here, it's root 101. Now the population at 30 will be 15 over root, and if I take 30 squared, that's 901. And you can see that this number is bigger than this because this denominator is so much bigger, which makes the fraction a lot smaller. So you can see how the population density is changing. More people at 10 kilometers than the density of people at 30 kilometers. So again, we set up the 2 pi r, which represents the circumference. Here's the thickness of the ring, and here's the density right here. And we go from 10 to 30. All right, your turn. Go ahead and stop the screencast and see if you can figure out the answer to the question. And here's the answer. Here's another opportunity. Stop the screencast, see if you can figure this out. And here's an answer. Okay, last, I want you to see that another application of this density is what we call flow rate. As blood moves or liquid moves through a tube, all the liquid does not move at the same rate. The particles appear closer to the walls are going to be slower than the particles that are flowing closer to the center, and that's because of friction. So the flow rate really depends, the velocity at which the particles are moving depends on the distance it is from the center of the tube. So flow rate is 2 pi r, but instead of density, it's going to be velocity, and that's going to tell us how fast all these particles are moving. So note the similarity in its derivation to that of population. And here's an example where it's being used.